This is my presentation for Lab 2, Projectile Motion. The purpose of this lab is to investigate the motion of a projectile by combining experimental observation, computational modeling, and data analysis. Altogether, we had to record and analyze the motion of a thrown object in 2 dimensions, model the motion computationally, and finally compare experimental results to theoretical predictions. First, we have the velocity update formula, which is derived from Newton's second law. This formula allows us to predict the velocity of an object as it moves through its trajectory. Next, we have the position update formula, which we can use in conjunction with the velocity update formula to predict the motion of an object. When the net force is constant, we use the arithmetic average of the initial and final velocity in place of v average. But when the net force is not constant, we assume v average to be equal to the final velocity in the equation. Gravity near the surface of the Earth is a constant force that always points downward, and it only impacts the y component of motion. The drag force is used in this lab to model air resistance, and b is a proportionality constant. This force always opposes the motion of an object and has a magnitude proportional to the square of the object's speed. Lastly, the net force on an object determines the acceleration. By Newton's second law, F net equals mass times acceleration. In the example shown, the forces along the y-axis cancel, so the net force is 0 in the y direction, but in the x direction there is a net force to the left, so the object will accelerate to the left. For key assumptions, we are ignoring any motion not in the x and y directions. We are also assuming external forces that are not due to air resistance or gravity to be negligible. And lastly, we assume that the calibration stick provides an accurate scale for converting video pixels to real-world distances. We utilized a meter stick in our video to ensure as much accuracy as possible here. And the key takeaway is that my experimental results confirm that gravity is not the only force impacting the projectile motion in this experiment. Tracker was used to track and analyze the motion of a paper ball acting as a projectile. This was the video that I inserted into Tracker. Take note that the system and the object whose movement is being tracked, in this case, that is the paper ball. The surroundings are everything else outside of the system that it can interact with. This includes air, gravity, the launch surface, or the table where the object lands. The experimental observations show results consistent with that of a projectile. For example, since the slope of the change in horizontal position versus change in time graph is constant, this means that the velocity in the horizontal direction was constant throughout the projectile's trajectory. On the contrary, since the slope of the change in vertical position versus change in time graph is not constant, that is consistent with the non-constant vertical velocity seen in projectile motion. Also, you can also see that when the object reaches its max vertical height, the slope is 0 in the bottom graph, indicating the y component of the velocity is 0 at the projectile's maximum height. The glow script simulation models a ball with mass 0.00095 kilograms that started at a position only in the y direction of 0.200 meters, with an initial velocity only in the x and y directions of 2.226 meters per second in the x direction and 0.4242 meters per second in the y direction. I started the clock at negative 0.2 seconds, and I used a timestamp of 0.033 seconds given by my tracker data. I set gravity equal to 9.8 meters per second squared, and I set my drag coefficient to be equal to 0.0005. However, when I modeled no drag force, I simply set this coefficient equal to 0, and overall the code includes gravity and air drag forces to calculate the net force and uses Newton's second law to update velocity and position. This is the results from the computational model that only accounted for the force of gravity, and since the force of gravity only acts in the y direction, the velocity in the x direction given by the slope of the graph on the left is constant. Now let's also account for air resistance by adding in the drag force. Remember, we did this by changing the proportionality constant in the code to a non-zero number. As you can see in these results, the slope in the graph on the left corresponding to the velocity in the x direction is no longer perfectly linear, indicating a net force component acting in the x direction. All models follow a somewhat parabolic path with regards to the projectile's trajectory. Additionally, all models show a slope equal to 0 in the y direction at the maximum height. Both computation models have the initial height as the max height, however, in the actual experiment, the max height was slightly higher than the initial height. The trajectory with no drag force reaches a greater horizontal displacement than the experimental observed trajectory, and the computational model that considers there to be a drag force. This is likely because without drag, the only force acting on the paper ball is gravity, and with nothing opposing its motion in the horizontal direction, the paper ball in the no drag model keeps its full horizontal velocity until it reaches the ground, allowing it to travel further in the horizontal direction. Potential sources of error that may account for the discrepancies seen are first, experimental design flaws. In the computational model, I used experimental y velocity, but the simulated paper ball did not reach the same height as the real one, suggesting missing factors. Next, the drag constant. I estimated this value with trial and error until the trajectory matched at y equals 0. And then finally, model assumptions. While the model includes air resistance, it assumes all other ideal conditions, such as no spin, no uneven throw, wobble, or shape changes, and this is unlike a real paper ball. So do any of the models predict a terminal velocity? None of my models predict a terminal velocity since there is a net force in each model impacting the motion of the projectile. But to find the terminal velocity of an object, you could perform a free fall experiment from a large height and track the object's velocity over time because the velocity will eventually level off and become constant since drag force will increase until it bounces the force of gravity, and then the net force will be zero. And then what if, say, I had thrown the object initially straight up? Well, if I had done this and the object had the same initial speed, the initial velocity would be entirely in the y direction. Thus, this object would reach a higher maximum height, so it would take a longer amount of time to reach the ground. Thank you.